All right, today we're going to tackle one of the most fundamental rules in all of electronics, Kirchhoff's current law. Now, you can think of it as kind of like the traffic law for electricity. It's this super powerful rule that tells us exactly what happens when different electrical paths meet up at a crossroads. So, let's ask that big question. What really happens when electric currents meet? I mean, do they crash? Do they just pile up? Or does some of the electricity just vanish? This is the exact puzzle that physicist Gustav Kirchhoff solved. And you know what? We're going to break it all down together. But before we can even get to the law itself, we need to understand the place where it all goes down. In electronics, we call this crossroads a node. And yeah, it might sound a little technical, but honestly, the idea behind it is something you see every single day. Okay, I want you to forget about electricity for just a second. Just picture a bunch of water pipes, right? You've got several pipes flowing into one single junction and a few other pipes flowing out. Now, what happens to all that water? It can't just disappear. The total amount of water flowing in has to be exactly the same as the total amount flowing out. I mean, where else would it go? This simple physical reality, that's the key to everything. And that junction, that's what we call a node. It's really just any point in a circuit where two or more wires or components meet up. So when we're talking about that electrical crossroads, we're really just talking about a node. It's the meeting point where our big traffic law applies. So now let's get to the law itself. See, Kirchhoff's idea wasn't just some random guess he made. He had this brilliant insight that the water pipe analogy holds true because of a deep fundamental law of physics, the conservation of charge. And here's the crucial point. Kirchhoff's current law, or KCL for short, says that electrical charge, the tiny electrons that make up the current, can't just be created out of thin air or destroyed at a node. Just like the water in our pipes, that current has nowhere else to go. It can't leak out, it can't just vanish. Every bit of it has to be accounted for. This brings us to the formal rule. To make the math work beautifully, we use this clever concept called an algebraic sum. It's really just a smart way of using positive and negative numbers to describe what's physically happening. So if we say everything coming in is positive and everything going out is negative, well, the grand total always has to be zero. It's like the universe's way of balancing its checkbook. Okay, so we've got the concept down. Now let's see how we turn this big idea into a powerful tool we can actually use. This is where we get into the math that makes KCL so incredibly useful for figuring out circuits. So to make that whole algebraic sum thing work, we just need one simple rule of the road. It's easy. Any current that flows into the node, we're going to call that a positive number. And any current that flows out of the node, we'll just call that a negative number. That's it. That's the entire trick right there. And when we apply that little sign rule, we get this beautifully simple equation. That big E-looking symbol, sigma, that just means the sum of. So this is really just a fancy way of saying what we already figured out with our water pipes. The sum of all the currents going in has to equal the sum of all the currents going out. Simple, right? All right, now for the really fun part. Let's put this law to work. See, the real power of KCL is that if we know most of the currents at a node, we can always, and I mean always, figure out the one we don't know. Let's give it a try. Okay, here's our little puzzle. We've got a total of 10 amps of current flowing into a node. From there, it splits and goes down 3 separate paths. Now, we've measured 2 of the outgoing currents. One is 2 amps and the other is 3.5 amps. But that third one, let's call it I2, is a total mystery. So, how do we find it? Well, we just follow the steps. First, we set up our KCL equation. The total current flowing in equals the sum of the 3 currents flowing out. Next, we plug in all the numbers we know. 10 amps goes in, 2 amps and 3.5 amps come out. We combine the currents we know on the right side, and we see that 10 amps equals 5.5 amps plus our mystery current. From here, it's just a tiny bit of simple algebra. And there it is. Our unknown current, I2, must be 4.5 amps. It's as simple as that. We just used a fundamental law of physics to find a missing piece of the puzzle. How cool is that? Okay, so solving for one current is great and all, but why is this one law so important? Why do we care so much? Let's zoom out for a second and look at the bigger picture. Why is KCL considered a cornerstone of, well, all modern electronics? Well, the power of KCL is that it's a rule you can always count on. It lets engineers analyze incredibly complex circuits. We're talking everything from your smartphone to a satellite with total confidence. It lets you troubleshoot problems, find those unknown values, and double-check that your circuit is actually working the way you designed it to. Seriously, every piece of circuit analysis software in the world has this law baked right into its very core. It is absolutely essential. So, we've totally mastered the crossroads. We know for a fact that what goes in must come out. But, that kind of brings up another question, doesn't it? KCL is perfect for a single point, for a node. But what about the journey? What law governs the energy of a current as it travels all the way around a complete circuit loop and gets back to where it started? Well, that, my friends, turns out to be the other half of the story.
Thanks for watching.